Well, we want to talk about superheat and we want to talk about reheat. We've been introduced to both of those, but let's do this. We come out of the boiler and we come across, we go into a turbine, and from the turbine, what is interesting for superheat is that it's not just saturated vapor here, it's superheated vapor. So that's the whole idea on the superheat. Why is it good, better for performance? More heat that's brought into the working fluid at high temperatures brings in less entropy. Hence, you have to throw out less entropy to the cold fluid, to the cold thermal reservoir. Hence, you throw out less thermal energy. Hence, it's just naturally going to be good for performance. More heat into the working fluid at high temperatures is always good for performance. Minimize heat in at low temperature into the working fluid. All right, so let's just finish this one out. After the turbine, what do you get? And then after the condenser, what do you get? Pump. And you have state 2, state 3, and state 4. Now, if you have reheat, you still have a boiler, and you're going to come out to a turbine. But what happens is you want to take and bring it down to an intermediate pressure, not the condenser pressure, some intermediate pressure. And maybe you draw it like this, where you then take it back to the boiler through a different set of tubes and then pass it through the second stage of the turbine. So we have the first turbine stage and the second turbine stage. You actually have multiple sections of the turbine. And in the real power plants, they do. They'll have typically 3. I don't think there's that many that have 4 or 5. It just gets ridiculous, the piping and etc. It's not like they have 5 or more turbine stages. They'll have the low pressure, high pressure for sure. Here would be a high pressure, low pressure section, and you could have intermediate. So once you come out, now you're at the condenser pressure. Put it through the pump, and away you go. All right, where will students get confused? And that's why I encourage you to do this. Draw a line like that through the boiler that connects what comes into the boiler with what goes out and into the first turbine stage. What does this little line right here indicate? You're picking up some heat in some of the tubes in the boiler. And these are a different set of tubes, and they're going to pick up some additional heat. And so you have to take that into account. There's 2 places where heat is transferred into the working fluid. Maybe this one is, you call that, I don't know, the first pass. And maybe you call this one the RH. What is the subscript RH for? Reheat, right? First pass and reheat. All right? All right. Let's introduce some states. It's common to put state 1 as the inlet to the first turbine stage. What comes out? State 2. Where is the most logical place for state 3? After the reheat, before the second turbine. And then state 4, then state 5, then state 6. True? All right. So that's reheat. Why, again, is that preferable? Why do real power plants have reheat? More heat at higher temperature coming into the cycle. It's going to be more efficient, higher thermal efficiency. Yes, so that's a good point. What is the difference between the pressure at 2 and the pressure at 3? Is it greater, equal, or less? I'm going to pause and walk around. All right, so it's our standard assumption that basically the reheat is just a heat exchanger where you're dumping more heat in, and what's the pressure drop of the working fluid through a heat exchanger? Standard assumption, all the way back to Thermo 1, negligible. Where do you have pressure gains? Pumps. Where do you have pressure losses? Turbines. You don't have pressure gains or losses in the boiler. Real boilers always have a little pressure drop because you're forcing it through. But usually you minimize it as an engineer. And so in our analysis for simplicity, we neglect it. All right. How about through the condenser? What's the difference between the pressure at 4 and the pressure at 5? Greater, equal, or less? equal, same idea. Same idea, true? All right, did that help you on your question about pressures? Very good. Well, here's a problem. And we have working fluid, ideal Rankine cycle, with superheated vapor enters the first turbine at 8 megapascal, 440 degrees C. It exits at 1 megapascal. It's reheated to 440, then enters the second turbine stage. And saturated liquid enters the pump at a pressure of 20 kilopascals. So, when you start to have reheat and 2 turbine stages, how many unique pressures are there for this system? 3. You just went from 2, only the boiler and the condenser, to 3 pressures, unique pressures. One is the intermediate pressure of the reheat. All right. Property values are not in any table. What is that written there for? Determine blah, blah, blah. This is a good illustration. What did I do? I introduced state 7 and 8 inside the boiler so I could tell how much energy is added between 6 and 7. It's going to be relatively cold. Have we solved this problem enough to know roughly the temperature of this water that's at 20 kilopascal, then goes through a pump and boosted back up to 8 megapascal? What is roughly, you recall, the temperature of that cold fluid? 60. Around 60 degrees C. To come up to state 7 where it's saturated liquid at 8 megapascal, what is the temperature of that fluid, state 7, saturated liquid 8 megapascal, from memory, roughly? 295 degrees C. Was there a significant increase in the temperature of the working fluid? Is it liquid at state 6, liquid at state 7? Yeah? There was a whole lot of heat just warming it up. Did it start to boil yet? But then it goes from saturated liquid to saturated vapor. What is the temperature of saturated vapor at state 8? 295. This is, again, I'll repeat it again and again and again. Most people say that can't happen. How can you pump heat into a working fluid and the temperature stay 295? Phase change. You're learning something. True? So anyway, then if it's go out superheated, what's the temperature at state 1? 440 degrees C. So what I do is I bust it into segments to help understand how much heat, just to get the water up to the boiling point, how much of that heat transfer to boil it, and then how much heat was used to superheat it on that first pass through the boiler. So that's why I introduced state 7 and 8, but otherwise 6 states is sufficient. What I'd like you to do is I would like you to plot this accurately on a TS diagram. With 7 and 8? No, without 7 and 8. You could put 7 and 8 on there if you like. So try and draw it as accurately as possible.
That answers my question.
All right, so let me pick it up here. So hopefully you memorized our numbers, right? And a few people will put state 1 right in this vicinity. Is that the location for state 1 in that vicinity? Because it's superheated coming out of the boiler, state 1. And so it's not near 300 or 295, the boiling point at 8 megapascal. They got the pressure right, but they need to get it up to around 440, don't they? So isn't state 1 right around there? And then some people will put state 2, they'll put it all the way down here. What's the problem with putting it down here? It's not the right pressure. We now have 3 pressures. It doesn't go all the way to condenser pressure. It goes to the intermediate pressure, which is at, for this problem, was it 1 megapascal? True or false? So if I expand it, and it will show around 98% quality. On the next page, we have the results. So it's in the 2-phase. Some people said, I think it may be superheated still. Well, as a design engineer, you probably want to get it to high quality. Get as much out of it as possible in that first turbine stage before you send it back to reheat. Now, when you send it to reheat from 2, it'll go quickly boil, heat up, heat up, heat up. What was the temperature coming out after reheat? Same as the other one, so 440. It's got to go all the way back up. Then you expand isotropically. Should the state 4 be maybe over here? What's the problem with putting state 4 over here? It needs to be isentropic below 3. Somebody put it way out here. What's wrong with state 4? It's the right pressure. It's not isotropic. Isotropic straight down on a TS diagram. Again, it'll come in at relatively high quality. That's the location of state 4. Where is state 5? Saturated liquid, way over here. That's 5. And then we put it through the pump, and we've spent a lot of time analyzing that pump. Is there a great temperature change across the pump? No. So essentially, it's a 0.5 degree C temperature change, if you just want to round it off. Well, on this scale, what's a 0.5 degree temperature change look like? So this is what I would do. I'd put a little arrow and say that's where state 6 is. It's so close to 5, I can't put 2 dots there to make them distinct. Make sense? So when it goes through the boiler, it's going to be heated at the constant pressure of 8 megapascal until it gets to be saturated. It's a little higher. Saturated liquid, and that is that state 7 that I introduced, that imaginary state somewhere in the boiler where it's now ready to boil. Then from 7 over to 8, it's going to boil from 8 to 1. Then we have the superheating. I'm going to show you some numbers on this, but I want you to give me your quick estimate of the fraction of the heat in percentages. Maybe you'll say that, oh, this takes only 10% of the heat, this takes 80% of the heat, and this is 10% of the heat. That adds up to 100%. See what I'm doing? What proportion of the heat brought into the working fluid in that boiler is just to get it up to the boiling point, then to convert it to boil, and then to superheat it. Can you just give me some estimates? Professor, I feel... All right, so I put you out of your comfort zone. I really asked as a percent, but mathematically, we know that Q that has to go into that boiler is going from 6 all the way to 1. I just add that subscript. Won't that be H1 minus H6? Isn't that how many kilojoules of heat added? And then I said, no. Find out what fraction of that heat. This is a probably bad symbol for fraction, but let me do this. Let's see Q that goes from 6 to 7. Divide that by Q from 6 to 1. Isn't Q 6 to 7? H7 minus H6. And you divide that by H1 minus H6. And that's going to be a percent, isn't it? And then we do the same thing. Q 7 to 8 divided by Q 6 to 1, sorry. That's going to be H8 minus H7 divided by H1 minus H6. And then the Q 8 to 1 divided by Q 6 to 1, which is H1 minus H8 divided by H1 minus H6. And these percentages, this fraction, and that fraction, all are going to have to add up to 100%. That's what I asked you to do. True? I'm going to take a few volunteers that say, I think my numbers are decent. Here's my numbers. What's your number?
Well, for the first one, it's 2%.
Oh, 2%? 2%?
Yeah, and I did 95%.
95%?
3%.
3%. All right, I'll take another volunteer. One more volunteer. Did I see a hand? Yes, sir.
We got 3% for the first one.
3%?
90% for the middle bit, and 7%.
7%.
For the rest.
One more volunteer. Yes, sir, in the back.
45%.
45%, and 10%. You know what? This just shows I asked you to really stretch your imagination, and let's go find out by going to the next slide. So what we did was we busted it into getting all of our states and all of our enthalpies. That's a table of properties. Then we had a table of transfers. And in the transfer, I busted the boiler going from 6 to 7, 7 to 8, 8 to 1. When I sum those three, it's nearly 3,000 kilojoules per kilogram. So it's 1,060 almost just to get it up to ready to boil. It is 35% of that total heat in just to get it ready to boil. Then 48%, a significant, the most of it is in the phase change. It takes a lot of energy to boil water. A lot of energy to boil water. And then only 16% to superheat. So of our three contenders, who was closest? Not bad. Okay, so anyway, there's having a little fun here. If we then compute the backwork ratio, it's 0.6%. That's great, and the thermal efficiency's improved a little bit above what we had before when we didn't have reheat. Okay? All right. A couple points worth pointing out. What will students often forget? That Q in the reheat. They'll start to calculate the thermal efficiency, this 37%, right? Looking at our numbers, is that 37% the net workout? Is it 1336.7 divided by the heat that's into the boiler, the 3000, which is 2980.6. If I give this problem on an exam, I'm telling you, I'm going to get a lot of students that'll say that is the thermal efficiency. Do you see why it's wrong? Do you see why it's wrong? I'm going to pause. I'm going to walk around and bye. Now this is what I'm asking for. The thermal efficiency of the cycle is, the numerator was right. That's the net work out of the cycle per kilogram going through the loop. But right here was the error. It was not just only the first pass through the boiler, but the reheat. And if we look, that's the number that I wanted to see you detect and put 601.7. That's what I was looking for. True? Got it. Do you know how often I have said stuff and then I find that I grade and it's the same error on the final exam? Here, I'm going to give you another one very quickly. Insert new page. Somebody earlier asked me a question. Hey, the specific heat for the whatever fluid, they give me a number, 4.18. It came in at kilojoules per kilogram degree C. But I don't need it in those units. I need that specific heat. And don't call out the answer. I'm going to walk around. I want everybody to solve this problem. I need the specific heat in kilojoules per kilogram Kelvin. Can you please convert that specific heat for me from these units to those units? And notice this is a specific heat of liquid water, 4.18, but that's irrelevant. It could be C sub P of air, C sub B of nitrogen. It could be a bunch of different specific heats. Don't get bogged down on that. Just convert the units for me, please. I'm going to walk around and check it. All right, I'm sorry, I'm going to run out of time. I'm going to have to pick it up here, okay? All right, somebody said, you know what? I'm going to multiply this by unit conversion. I'm going to multiply by, let's see, Kelvin, degree C. Okay, I'm going to take, I can't remember that conversion. They said temperature, degree C, I add 273.15. That's temperature and degree without the degree symbol, Kelvin. I think I remember an equation like that. So what I'm going to do is I'm going to put temperature, degree C, okay, and I'll divide by temperature in Kelvin plus 273, no, minus 273, 0.15. Is something like that correct? See a lot of people trying it. It's not correct. No, it's not correct. Then I see somebody over here, I think they did it. They said, you know, I think 1 degree C equal to 1 Kelvin. So I'm going to just do this. I'm going to multiply 1 degree C by 1 Kelvin. Cancel. The answer is 4.18. Are they right? I have to explain this every semester. Any class I teach. It goes back to this illustration in chapter 1, I believe, of this textbook, but it's in many, many, many textbooks. And it says, we're going to talk about temperature scales. And when you have a high value of temperature, that indicates hot. A low value of temperature, that indicates cold. And we have 4 languages for temperature that we should be fluent in as engineers. One is degree C, one is K, Both of these are what they call the international. And then we in the U.S. customary system. We still have degrees F. And the fourth one, which isn't much around, but it's degrees R. True or false? Have you seen an illustration like this? And they say, you know what? We have this common coldness, hotness, and it's called water's ice point. It's where water freezes. The freezing point. Freeze of water, H2O. And they come over here and they say, I remember the value of the ice point of water in degrees C. What is that? See, you know temperature, 0. And then they put over here, hot water, B-O-I-L-S. Boils, the boiling point of water. What temperature does it boil at in degrees C? 100. Does this look familiar? They could talk about the whole scale going in between there. They add 273. They add 273, but let's not get bogged down on the Kelvin right now. But let's get over here. What is it over here? It's 32,212, right? This illustration's in your high school chemistry book. This illustration's in your physics book. And yet, you need to dominate it. Because from this, we can see that there's 100 degree C temperature change between the 2 points. There is, how many? 180 degree F change. So sometimes you'll see this written. You'll see that 100 degree C temperature change is exactly 180 degree F temperature change. Is that equation correct? Is that equation correct? When you're talking about temperature change, it's exactly correct. But it's not the same to say 100 C is equal to 180 F. If you're talking about the magnitude of the temperature, 100 degrees C is equal to 212 degrees F. You say these contradict. Well, one is talking about a temperature change and one's talking about the magnitude of the temperature. Well, what are we doing with this degree C right there? Is that the magnitude of the temperature in the specific heat, or is it the temperature change in the specific heat? It's the temperature change in the specific heat. And 1 degree C temperature change is precisely 1 degree K temperature change. Look at the definition of specific heats. Isn't it something like the rate of change of enthalpy with respect to temperature as something holds constant? Like pressure is constant? It's how that value changes with respect to temperature. It's a temperature change. This is correct. Thank you for your attention. Done for today.